What if I told you that the greatest mysteries, the most profound secrets of the universe, are not light years away in distant galaxies, but right here, hidden in plain sight? Look around you. Really look. What do you see? Maybe you see a simple, beautiful flower, its petals unfurling towards the sun, a splash of color against the green. That's one perspective, the surface view, lovely and easy to grasp. It's the everyday world we navigate, solid ground, predictable objects, the familiar flow of time. But what happens when you lean in closer? What happens when you look deeply? Not just at the intricate pattern of veins on a single leaf, or the delicate structure of a stamen, but beyond, past the visible, past what your eyes can perceive. Suddenly, that simple flower transforms. You begin to see not just a single entity, but a complex tapestry woven from countless threads. You see the water drawn up from the soil, the sunlight captured and transformed into energy, the very air breathed in and out. You see the nutrients that fed its growth, the microscopic organisms in the earth supporting its roots, the ancient stardust that forms its very atoms. You begin to see the whole picture, or at least, a much larger, more intricate piece of it. It's a layered reality, far richer and more complex than the surface suggests. This idea of looking deeper, of seeing the underlying structure and interconnectedness of things, isn't just a philosophical exercise or a poetic metaphor. It is, in fact, the key to understanding the very fabric of our reality, the principles that quietly, constantly, build and connect our world at the most fundamental level. These aren't abstract concepts confined to dusty textbooks. They are the dynamic forces that govern the behavior of everything around us. The chair you're sitting on, the screen you're looking at, the air you're breathing, and yes, even that seemingly simple flower. These principles have a name that might sound complex, perhaps even a little intimidating: quantum mechanics. But don't let the name scare you. Think of it not as a rigid alien concept, but as the fundamental language of nature at its smallest scales. If the world we see every day operates on the rules of classical physics, like how a thrown ball follows a predictable arc, the world down at the molecular and atomic level operates differently. It's a world of probabilities, of particles that can be in multiple places at once, of energy existing in discrete packets, of interactions that seem almost magical from our everyday perspective. These quantum principles are the invisible architects, tirelessly building and connecting our world, atom by atom, molecule by molecule. They govern how atoms bond to form molecules, how light interacts with matter, how energy flows, how everything, from the hardness of a rock to the fragrance of a flower, ultimately behaves. They are the deep code running the simulation of our reality. For generations, we have studied these principles, first observing their effects in nature, then meticulously trying to understand their rules. And over time, a revolutionary thought emerged. If these fundamental principles are what govern the universe at its core, could we harness them? Could we take this deep, almost mystical understanding of how nature works at its most profound level and use it? Not just to understand the flower, but to create something entirely new, something that operates on these very rules. This line of thinking led to an extraordinary leap in human ingenuity. It led to the concept, and now the dawning reality, of quantum computing. Imagine a computer built not on the simple, binary on or off switches of traditional computers, but on the strange, layered, interconnected principles of quantum mechanics itself. Imagine a machine that can hold information not just as a definitive 0 or 1, but as a combination of both simultaneously, or in complex, entangled states that are linked together in ways that defy our everyday logic. When the same principles that govern the behavior of matter and energy at the molecular level are harnessed to power a computer, we unlock a capability fundamentally different from anything that has come before. We unlock the potential to find solutions for problems that were once considered, quite literally, unsolvable. Why unsolvable? Think about the complexity of nature itself. A living cell, for instance, is an unimaginably intricate machine, with billions of atoms interacting in dynamic, constantly changing ways. Trying to model this complexity using a classical computer is like trying to count every grain of sand on every beach in the world simultaneously, while also predicting the path of every single wave hitting the shore. The number of variables, the sheer scale of the interactions, becomes so vast, so exponentially complex, that even the most powerful supercomputers we have today grind to a halt. There simply isn't enough computing power in the known universe, using classical methods, to tackle certain types of problems. These are the otherwise unsolvable problems, challenges that involve understanding and simulating complex systems at their fundamental quantum level. Let's bring this down to a concrete and incredibly important example, one that is happening inside your body right now as you listen to this. Have you ever taken a medicine? An aspirin for a headache, an antibiotic for an infection, a pill for blood pressure? We often take these things for granted, trusting they will do their job. But how does your body handle these foreign substances once they enter your bloodstream? It's a complex, fascinating process, and an absolutely critical player in that process is an enzyme called Cytochrome P450. Now, most people haven't heard of Cytochrome P450. It's not exactly a household name, but this enzyme is a quiet, essential hero in your internal chemical processing plant, primarily located in your liver, but also in other tissues. Its job is like that of a molecular mechanic, specialized in breaking down substances that the body doesn't recognize as its own, things like toxins, environmental pollutants, and yes, most of the medications we take. It chemically transforms these substances, often making them easier for the body to excrete or less harmful. This enzyme plays an absolutely essential role in how medicine works or doesn't work for you. Think about it. For a drug to be effective and safe, it needs to be absorbed, distributed, and then ultimately metabolized and eliminated by the body. Cytochrome P450 enzymes are responsible for metabolizing roughly 75% of all currently marketed drugs. Understanding how a potential new medication interacts with Cytochrome P450 and which specific variants of this enzyme it interacts with, because there are many, is not just important, it is a critical, absolutely non-negotiable step in the long, arduous journey of drug development. Why is it so critical? Because these interactions determine several vital things. 1. How fast is the drug broken down? If it's broken down too quickly, it might not stay in the body long enough to have its intended effect. If it's broken down too slowly, it could build up to toxic levels. 2. Are there active or toxic byproducts created? Sometimes, when Cytochrome P450 breaks down a drug, it creates new molecules. Some of these metabolites can be the actual active form of the drug, others can be inactive, and crucially, some can be toxic and cause dangerous side effects. 3. How might the drug interact with other drugs? This is huge. If drug A is metabolized by a specific Cytochrome P450 enzyme, and you take drug B that either blocks or speeds up that same enzyme, it can dramatically alter how your body processes drug A, potentially leading to either dangerously high levels of drug A or making it ineffective. This is the basis of many dangerous drug-drug interactions. 4. How might genetics affect drug response? People have genetic variations that affect how their Cytochrome P450 enzymes function. Some people are fast metabolizers, others are slow metabolizers. This is why the same dose of a drug can work perfectly for one person, require a much higher dose for another, and be toxic for a third. So, predicting and understanding the intricate dance between a new drug molecule and the various forms of the Cytochrome P450 enzyme is fundamental to developing safe and effective medicines. It helps researchers design better drugs, predict potential side effects, and understand why different people might respond differently. It's a cornerstone of what we hope will increasingly become personalized medicine, tailoring treatments to an individual's unique genetic makeup and metabolic profile. But here's the challenge, the unsolvable problem for classical computers: accurately modeling the interaction between even one drug molecule and one variant of the Cytochrome P450 enzyme at the atomic and molecular level is incredibly computationally intensive. You have to consider the precise 3D structure of both molecules, the positions of all their atoms, the complex network of forces between them, which, remember, are governed by those deep quantum principles. How those forces change as the molecules approach each other, potentially bind, and undergo chemical transformation. The number of possible arrangements and interactions is astronomical, mind-bogglingly large. Simulating just a tiny fraction of these possibilities with enough accuracy to be truly useful can take classical supercomputers weeks, months, or even prove impossible within a practical time frame. This bottleneck significantly slows down the drug discovery and development process, making it incredibly expensive and time-consuming, often taking over a decade and billions of dollars to bring a single new drug to market. This is precisely where the unique power of quantum computers comes into play. Because quantum computers are built using the same fundamental principles, the rules of quantum mechanics, that govern the behavior of molecules and their interactions, they are inherently suited to simulating these complex systems. Unlike classical computers that struggle to represent the layered, probabilistic nature of molecular interactions, quantum computers are designed to handle it. Scientists at Google Quantum AI, among others in this cutting-edge field, have been working on this very challenge. They have shown through groundbreaking research that quantum computers will be able to more effectively model these complex interactions, including those involving enzymes like Cytochrome P450. They've demonstrated the potential for quantum algorithms to accurately simulate molecular behavior in ways that are currently out of reach for classical computation, opening up a new pathway to understanding these vital biological processes. What does more effectively model mean in this context? It means being able to simulate the process faster, with greater accuracy, and for more complex molecules than ever before. It means being able to explore a wider range of potential drug candidates and predict their behavior with Cytochrome P450 enzymes much earlier in the development pipeline. This isn't just a technical improvement, it's a potential paradigm shift. Being able to rapidly and accurately predict these interactions could dramatically accelerate discoveries in medicine. Promising new drug candidates could be identified and validated faster. Dangerous drug-drug interactions might be predicted before they ever happen in a patient. Personalized dosing based on an individual's metabolism could become a more routine reality. And Cytochrome P450 is just one example. This capability to effectively model complex molecular interactions has implications far beyond this single enzyme. It could accelerate the discovery of new materials with amazing properties, lead to the design of more efficient catalysts for chemical reactions, help us understand and combat climate change by modeling complex atmospheric chemistry, and pave the way for bigger breakthroughs across countless scientific and industrial fields. Google Quantum AI is not just building incredibly complex machines. They are on a journey to unlock the profound potential of quantum computing. They are exploring the frontiers of computation, pushing the boundaries of what's possible, specifically to find solutions for problems that were once deemed impossible. Problems that, when solved, have the potential to profoundly impact our health, our environment, and our future. So, what can we take away from this incredible journey into the quantum realm and its potential to heal? Perhaps the most important lesson is the power of looking deeper. The flower that seems simple on the surface is a universe of complexity and wonder when viewed through the lens of fundamental principles. The processes happening unseen inside our bodies, like the work of Cytochrome P450, are intricate and essential, governed by the same deep rules that shape the stars. It reminds us that when we encounter something complex, something seemingly unsolvable in our own lives, a difficult relationship, a challenging career hurdle, a personal health mystery, the solution might not lie in just trying harder with the same approach, but in trying to understand the underlying fundamental principles at play. What are the core dynamics? What are the hidden interactions? What are the rules, spoken or unspoken, governing the situation? By seeking that deeper understanding, by looking past the surface symptoms to the root causes, we gain clarity and unlock new possibilities. Don't be intimidated by complexity, whether it's quantum mechanics or a personal challenge. Approach it with curiosity. Ask questions. Seek to understand the fundamental principles that govern it, because within that deeper understanding lies the potential for innovation, for healing, for growth, and for finding solutions that once seemed impossible. The universe, in all its intricate beauty, is waiting for us to look deeper. What hidden complexities are you overlooking in your own life or the world around you? Where might a new perspective, a deeper look at fundamental principles, unlock a seemingly impossible challenge you face? What incredible solutions might be waiting to be discovered if we all committed to looking beyond the surface? Until next time, I wish you the very best of health, courage in the face of complexity, and clarity in seeing the world, both the obvious and the hidden. If this journey into the deep principles of nature and technology resonated with you, and you're curious about the incredible ways science is shaping our future, please consider subscribing to join our exploration. Let's keep discovering together.